Hello, everyone, and welcome to our presentation on the impact of microgravity on the efficiency of antibiotics produced from fungi.
I'm Carolyn, and I'm from Boston, Mass.
I'm Suhani, and I'm from Austin, Texas.
I'm Noelle, and I'm from the Woodlands, Texas.
And I'm Leah, and I'm from Fort Worth, Texas.
Our experiment looks at the effectiveness of antibiotics derived from the fungi Penicillium chrysogenum, grown in microgravity on the International Space Station, and their effectiveness against potentially harmful bacteria. We all had an interest in biology, medicine, and space, and we wanted to create a project that would combine these interests. We learned through the C's Speaker series that fungi have a faster growth rate in space, and through research, we found that fungi could withstand radiation up to 200 times the dosage that would be fatal to a human. So we were interested in designing an experiment that could harness these unique capabilities of fungi to enhance antibiotic production to improve long-term space travel. Fungi are found in multiple habitats, and the CDC estimates there are 1.5 million species of fungi on Earth. Fungi are also involved in the production of more than 10 of the 20 most profitable products in medicine. For our experiment, we decided to use the fungi Penicillium chrysogenum, which produces antibiotic penicillin. We decided to choose penicillium as the fungi for our experiment due to its low ability to cause invasive diseases, as well as its popularity and well-established reputation in the medical industry.
In our hypothesis, we believe that if Penicillium carcinogenum is produced on the ISS and then synthesized for antibiotics, then it can be concluded that the antibiotic strength in space is equally effective as it is on Earth, and this is because Penicillium carcinogenum can flourish and thrive in conditions on the ISS.
Now I'm going to walk you through the procedure for the experiment. 2 sets of samples of Penicillium chrysogenum will be sent to the ISS, while 2 sets of control samples remain on Earth. Both sets of samples will be kept at the same temperature and both in potato dextrose. 1 week after being sent to the ISS, 1 set of samples will be grown and synthesized into penicillin, which will then be sent back down to Earth. At the same time, 1 set of control samples will be grown and synthesized into penicillin. When both of the first round of penicillin samples are on Earth, their effectiveness will be tested with the disk diffusion assay, measuring the zone of inhibition. The image on the side is an example of this assay, and we would measure the diameter of the circle of fungal inhibition around the antibiotic disk. The second set of samples will be kept in dormancy for 3 months, so the experimental sample can fully adapt to the unique environment of microgravity. Then the remaining set of samples and the corresponding control set will be synthesized using the same procedure. When both of these second round of penicillin samples are ready, their effectiveness will be tested. And this is an example of what the data table would look like when we had actual numbers and data to go in there.
Humanity is headed towards the stars. For future missions, especially long, deep space ones like Mars, it may be vital to have the ability to combat sickness. For these missions, it's generally not very energy efficient to bring months or years worth of medicine from Earth into space. If our hypothesis is proven correct, it would imply it's viable for those going on deep space missions to bring up a small amount of materials like penicillium used to make medicine and simply keep replenishing the supply on board whenever needed. This would allow astronauts to be able to synthesize antibiotics they may need in space without much cumulative energy costs from bringing materials from Earth. This not only has applications for those in space, but for those on Earth as well. If materials grown for antibiotic production in space prove just as or more effective than those grown on Earth, this could be quite impactful for pharmaceutical companies. Scientists already recognize that microorganisms grow more rapidly in space. However, if materials synthesized from these space-grown organisms were equally or more effective than those on Earth, this would allow these companies to increase efficient remedy production, allowing more people access to vital medications when they need it.
William Arthur Ward once said, feeling gratitude and not expressing it is like wrapping a present and not giving it. So as we wrap up our presentation, we would like to give thanks to everyone who made it possible for us to be a part of this program and to learn so many wonderful insights in this amazing world of science. Thank you to Ms. Foxworth, Ms. Baggio, Ms. Miller, Ms. Henry, Dr. Redberg, guest speakers, C's program as a whole, and to all the viewers watching. We want to say thank you. Here are our highlights. And here are our wonderful reflections. And these are references. Thank you again for listening to our presentation.